Good afternoon, students. In today's class, we will study about AC power analysis. The contents of this chapter are: first, we'll discuss about instantaneous and average power, maximum average power transfer, effective RMS power, apparent power and power factor, complex power, conservation of AC power, power factor correction. These are some of the topics we will see in this chapter. Okay, instantaneous and average power. So what is instantaneous power and what is an average power? Suppose I have here a source, voltage source. Then there is here a network, a passive network element consisting of, for example, resistors, capacitors, inductors. The voltage across the passive network is V of t, and the current going to the network is I of t. The voltage across the network is in time domain given by Vm cosine omega t plus theta v, where theta v is the phase of the voltage V of t. And the current I of t is given by I of m cosine of omega t plus theta I. Theta I is also the angle. Now, what is the instantaneous power? The instantaneous power P of t is equal to V of t times I of t is equal to Vm times Im cosine of omega t plus theta v cosine of omega t plus theta I. Now, from trigonometric property, if I have cosine of A times cosine of B, this is equal to 1 over 2 cosine of A minus B plus cosine of A plus B. So let's say if I have A is omega t plus theta V and the other angle B is omega t plus theta I. So A plus B will be this one and A minus B will be omega t cancel omega t theta V minus theta I. And there is 1 over 2 here. So because of that, we have 1 over 2. So it will be 1 over 2 Vm Im cosine of theta v minus theta I plus 1 over 2 Vm Im cosine of 2 times omega t plus theta v plus theta I. This part, as you see, it is a function of time. A function of time, and it is a sinusoidal power with frequency 2 times omega. Why it becomes 2 times omega? Because of the multiplication, when we do the multiplication. And this part is constant because it is just cosine, theta v is constant angle, theta I constant angle, so cosine of a certain constant angle, then this factor is constant. This is the constant power. So we call this is the average power. So if I plot the power as a function of time, okay, P of t, the instantaneous power as a function of time, we'll have a constant part plus an AC part. So if I plot it as a function of time, it looks like this. This is function of time and the wave like this. Now, if it was AC, should have been symmetric about 0. But because we have this constant part adding, then it will be shifted vertically shifted by 1 over 2 times Vm Im cos theta v minus theta I. When P of t is positive, that is P of t greater than 0, we call power is absorbed by this circuit. And when P of t is negative, if P of t is negative, power is absorbed by the source. Because remember from first chapter about positive power and negative power convention. When positive, it is power absorbed by the circuit. When it is negative, power will be delivered. So in this case, the circuit delivers power to the source by the source. Power is transferred from the circuit to the source. This is possible because because of the storage elements. For example, if I have capacitors and inductors in the circuit, then they can transfer energy to the source. So the instantaneous power, it changes with time, and added to it is the average power. This is the average power. We said the constant part is average power. Basically, how we calculated the average power? Very easy. If we integrate the overall function, this P of t, over one period, and integrate from 0 to t divided by the period t, we'll get the result. So the integration of this over one period is 1 over t from 0 to t, the integration of the constant part plus the integration of the AC part. The integration of the constant part, because this is constant, it doesn't depend on t, then this will be t, and evaluate from capital T to 0, it will be t, and t will cancel t, and it will give me the same constant number. So the integration of the constant number will be the constant. What about the integration of the AC part, this part? The integration of the AC part, evaluate from 0 to t, this cosine will become sine. But when I evaluate from 0 to t, you can try it, it will become 0. It will become 0. So the AC part, the average part of the AC part will become 0. The first integrand is constant, and the average of a constant is the same constant. The second integrand is a sinusoid, and the average of a sinusoid over its period is 0, which means the average of the instantaneous power over one period will give me the constant part, which is 1 over 2 Vm Im cos of theta v minus theta I. Now we can also calculate the average power from using phasor representation. We can represent, for example, the voltage V of t is equal to Vm at an angle of theta v. The current I is equal to Im at an angle of theta I. This is called phasor representation, as you know. Then 1 over 2, the power, the complex power will become 1 over 2 V times I conjugate. 1 over 2 V times I conjugate, this means 1 over 2 times Vm Im. So the angle is conjugate, means theta I will be minus theta I. So it will be theta V minus theta I when we add the two angles after the conjugate. Then we have the complex power is 1 over 2 Vm Im cosine of theta V minus theta I plus J sine of theta V minus theta I using Euler identity. Now, the average part is given by this formula. P, the average power, is equal to 1 over 2 real part of V times I conjugate, the real part of this complex power. The real part is obviously this one. So it will be 1 over 2 Vm Im cosine of theta V minus theta I. So the average power is not time dependent. And if theta V is equal to theta I, if the angle theta V is equal to theta I, we call the voltage and the current are in phase. For what kind of element? For a resistor, for example. The current through the resistor and the voltage across the resistor are in phase. So theta V is equal to theta I, and it will be purely a resistive load. And cosine of 0 will become 1, then it will be simply 1 over 2 Vm times Im. If the voltage theta V minus theta I is equal to positive 90 degree, which is if I have inductive load, inductor. Remember, the inductor voltage in phasor domain is V is equal to J omega L times I. So the inductor voltage leads the inductor current by 90 degree. So theta V minus theta is 90 degree, and cosine of 90 degree will become 0, and again the average power will become 0. And for the capacitive load also the same, theta V minus theta I is minus 90 because the current leads the voltage for the capacitive load, for the capacitor case. Then again cosine of minus 90 degree is 0. Then P is equal to 0, means that the circuit absorbs no average power. Okay, now let's do some examples. Example, find the instantaneous power and the average power absorbed by a passive linear network if the voltage is this one and the current is this one. So the voltage is 120 cosine of this 770 plus 45, the current 10 cosine of this. So if you see here, what is the angle? The angle is 45. So the voltage leads the current by 45 minus 10, 55 degree. So the instantaneous power is simply we multiply 120 times this 1200 cosine of 377 t plus 45 cosine of 377 t minus 10 degree, and applying again this trigonometric identity that we said before, we have P is equal to 600 cosine of 754 t plus 35 plus cosine of 35 degree, 600 times everything. So the average power will become this one. Or we can just directly use the formula. P is equal to 1 over 2 Vm cosine of theta V minus theta I. So 120 is Vm, Im is 10. Then we replace this, and again we will get the same result, 344.2 watt. So for the instantaneous, we need the time domain factor here, T, so we just directly multiply the two. Calculate, this is a practice problem, calculate the instantaneous power and the average power absorbed by the passive linear network if V of t is given by this and I of t is given by this. Note that here I of t is a sine function, so we need to change it to cosine. How we change? We use the rule of sine theta is equal to cosine of theta minus 90 degree. So here we have to change this to cosine, so minus 90 degree here, and it will be 15 cosine of 10t minus 30 degree. And then we apply the formula, we can get the average power like this, and the instantaneous power given by this. This is another example. Calculate the average power absorbed by an impedance. This is an impedance having Z is equal to 30 minus J70 ohm when a voltage applied across the load is 120 at an angle of 0 degree. So we have the load here. This is capacitive load because I have minus J30 minus J70. What is the current? The current through the impedance is I is equal to V over Z. Okay, V over Z. So we change Z to phasor form. Okay, so magnitude is this, and the phase angle is this. Remember the phase angle minus 66.8 degree. Why? Because here the imaginary part is negative and the real part is positive. So if you think about the quadrants, the XY axis quadrant, first quadrant, second quadrant, third quadrant, and fourth quadrant. So this is in the fourth quadrant. So that's why I have minus 66.8 degree. So the average power now, this is phasor representation. So this is Vm. Okay, this is angle, this is Vm, and this is this is Im, and this is Vm 120. So P, the average power, is 1 over 2 Vm Im cosine of theta V minus theta I is equal to 1 over 2 120 times 1.576 cosine of 0 minus 66.8, which will become this one. Now this is also another example for the circuit shown in this figure. Find the average power supplied by the source and the average power absorbed by the resistor. Okay. What is the average power supplied by the source? Now again we determine the phasor current. The current I is 5 at an angle of 30 degrees over the total impedance. The total impedance is 4 minus J2. 4 minus J2, then we change it to phasor form like this, and we get this. So this is the phasor representation of the current. This is Im, and this is the angle. Then the average supplied power is 1 over 2 times the voltage Vm and Im, and the angle between the two is 30 minus 56.7, which is equal to 2.5 watt. Now, what is the current through the resistor? It's the same because it is a series circuit, and I have the current through the resistor is this. What is the voltage through across the resistor? The voltage across the resistor is the resistance times the current, and I have this. So what do we notice here? We can see that the phase angle of the current is the same as the phase angle of the voltage. Why? Because the voltage and the current are in phase for a resistor. So that's why. So there is no angle difference between this. Then what's the power delivered to the resistor? Half times Vm, which is 4.472, times Im, 1.18, cosine of 0. The angle, there is no phase difference between the two, cosine of 0, which will give me this one. The power is 2.5 watt. Now, if we see the power delivered, supplied by the source is equal to the power absorbed by the resistor. 2.5 watt, 2.5 watt. Why? Because the capacitor does not absorb the power, okay? Does not absorb the power. That's why, because this is only the resistor will dissipate it. So the average power supplied by the source is equal to the power absorbed by the resistor, and zero average power is absorbed by the capacitor. Okay, this is practice problem. Current is given. Again, impedance is given. Find the average power delivered to the impedance. And this is also straightforward, not difficult. You can do it. Okay. And this is another practice problem. Calculate the average power absorbed by each of the 5 elements in the circuit of the following figure. Now, what is average power absorbed by each element? By the source, by the resistor, by the inductor, by the capacitor. So you will do the same thing. You will try to analyze this circuit. You can use any you can use nodal analysis, mesh analysis, or any of the circuit analysis techniques to solve this problem. But here is, for example, if you see the solution here, the voltage source, the 40 volt here, the power absorbed is minus 60 watt. The power absorbed minus 60 means it is supplied. So it is supplying the power. And the power by this source, the power supplied by this source is minus, absorbed by this source is minus 40, means it is supplying the power. And the power absorbed by the resistor, this is 100 watt. And the power absorbed by the other elements, for example, by the inductor is 0, by the capacitor is 0, because they don't have average power. They don't consume average power. So that means the power supplied by the two sources, which is 60 plus 40, will be the power absorbed by the resistor, the 8 ohm resistor, which is equal to 100 watt. Okay, maximum average power transfer. When do we say maximum power is transferred to the load? Or how can we design a load so that it will absorb maximum power from any linear circuit? This is called the maximum power transfer criteria. So the maximum power transfer criteria says, if, for example, this is a linear circuit and a load is connected, ZL, and if I find the equivalent circuit of this, the linear circuit, remember from Thevenin theorem, we can represent it by V Thevenin and Z Thevenin. I have V Thevenin here, Z Thevenin for this circuit, for the left part, and I have the load here. Then what is the relation between the load and Z Thevenin? So for the load to absorb the maximum power, or for the supply voltage to transfer maximum power to the load, ZL, which is equal to RL plus JXL, is equal to Z Thevenin conjugate. Z Thevenin conjugate, where Z Thevenin is R Thevenin plus JX Thevenin. So in that case, what does it mean? If I take the conjugate of ZL is equal to Z Thevenin conjugate, it means XL will be minus X Thevenin. So XL is equal to minus X Thevenin and RL is equal to R Thevenin. During this scenario, what will be the current through this circuit? The current will be V Thevenin over Z Thevenin plus ZL. Add these two. When we add Z Thevenin plus ZL, the J parts will be 0. Why? Because XL is equal to minus XT. So if I add these two, the J part will cancel. And RL is equal to R Thevenin. So it will become 2 times R Thevenin. So the current through the circuit will be V Thevenin over 2 times R Thevenin. So if we try to find the power, okay, we found now the current, and we can find the voltage across the load by voltage division. The voltage across the load is VL is equal to V Thevenin times ZL over Z Thevenin plus ZL, okay? And keeping in mind the relation between Z Thevenin and ZL. And after we find the voltage across the load and the current, if we use the formula, the power is 1 over 2, the power delivered to the load is 1 over 2 real of V load times I conjugate, which is the current through the ZL and Z Thevenin. We'll find the maximum power is equal to absolute value of V Thevenin square over 8 times R Thevenin. 8 times R Thevenin. It's very easy. You can try to do this. But if you have a problem, you can always ask me. So it's very easy. We already found the current, and then what you do is find the voltage, and then use the formula P is equal to 1 over 2 real of V load times I conjugate. So you will get this formula. Now, what is the difference between this formula and the formula we studied in the previous chapter 4, for maximum power transfer? Okay, in that case, we were having purely a resistive load, and it was 4 times RL. So P max is V Thevenin square over 4 times R Thevenin, or 4 times RL. So why in this chapter it becomes 8 times, in the previous chapter 4 times? Because in this chapter we are dealing with AC, and for the AC we have 1 over 2 factor. Remember the 1 over 2, the formula when we try to have the formula for the power, we have P is equal to 1 over 2 times real of V times I conjugate. Because of this 1 over 2 factor, we will have 2 times 4 and 8. That's why it becomes 8 in this calculation. If the load is purely a resistive load, a real load, then RL should be square root of R Thevenin square plus X Thevenin square, which is the magnitude of Z Thevenin. Okay, this is the criteria of the maximum power. For today, let's do this example again, and then we'll continue the rest of the topics. So example 4, determine the load impedance ZL that maximizes the average power drawn from the circuit in the figure below. What is the average maximum power? Okay, now I have here a source and I have a load here. So we need to find the load impedance that maximizes power transfer from the source to the load. And it's obvious ZL should be equal to Z Thevenin. So we need to find Z Thevenin. So how do we find? There is a source here, we short this source. And we disconnect the load and we'll find the Thevenin impedance looking to the left like this. So we short it. So what will become now? 8 and minus J6 are in series, and it will be in parallel with 4 ohm. And then everything will be in series with J5. So Z7N is J5 plus 4 in parallel with 8 minus J6. So J5 plus 4 for the parallel combination, the equivalent impedance is this 4 times 8 minus J6 over 4 plus 8 minus J6. And finally, we will find this one. So this is R Thevenin and this is Z Thevenin. So we find Z Thevenin. So Z load should be Z Thevenin conjugate. Of course, this will be minus. Now, what is V Thevenin? V Thevenin, we open the load. By opening the load, what will be? There is no current here. Therefore, it will be voltage division between 4 ohm and 8 minus J6. So V Thevenin is 8 minus J6 times 10 over 4 plus 8 minus J6, which will become this one. Okay, so this is V Thevenin. So we find the V Thevenin. So the load impedance that draws the maximum power from the circuit will be ZL equals to Z Thevenin conjugate. So this will be minus. The maximum average power is the absolute value of V Thevenin square over 8 times R Thevenin. So we found already V Thevenin. The magnitude of this is 7.454 whole square over 8 times 2 times 9.33 because this is R Thevenin, and we get the power 2.368 watt. So that's all about today's class. We'll continue the rest of the topics in the next lecture. Please try to redo the examples and to have more understanding. It's always important to do the practice problems and also redo the examples. Thank you for listening to this lecture.